We changed the memo to the CFD.
Okay, we're all set up here, I think, with the video links, so we might as well start today's continuing lecture on data analysis. I just wanted to pick up where we left off last time in our discussion of hypothesis testing. Recall that we had translated a null hypothesis into a test statistic and then calculated how probable it was to observe the measured test statistic. And that gave us a p-value which possibly could have refuted the null hypothesis. And generally, I mentioned the threshold for refuting the null hypothesis was around 5% or so. The first example we did of calculating a p-value was just using the central limit theorem when we had a null hypothesis which specified the mean of a random variable and then measured some data. After taking the sample mean and rescaling it by the sample variance and square root of n, we came up with this value for our test statistic, 0.289. Of course, the p-value can then be calculated by using the cumulative distribution function of the Gaussian random variable. So we want to define the p-value as the probability that we obtain a test statistic at least as deviant as the one we observed. So we integrate from the one we observed up to infinity. You can change this around into the error function, which is the definite integral of the Gaussian distribution. And then we get a reasonable p-value which does not lead us to refute the null hypothesis. So a more complicated hypothesis that you might specify for the data is an entire specification of the PDF rather than just the mean. So if you have a discrete PDF, a test statistic which you can use is the chi-square. And if you have a continuous PDF, you have to perform this KS test, which we'll talk about today. So first, the chi-square. This is just from last time. If you have a discrete random variable which you would like to specify the PDF for, that's that P of K there. Then you perform the experiment and you get a bunch of results for each of the different outcomes. Those are these n's here. You can construct this chi-squared test statistic, which is generally the expected minus the observed divided by the expected, well, squared divided by the expected. And this chi-square should be distributed according to the chi-squared distribution with n-1 degrees of freedom. The PDF of this distribution is given here, and the CDF is given here in terms of this incomplete gamma function. So armed with knowledge of the CDF, you can use the chi-squared to calculate p-values, illustrated by this example here. Say we have some 5-sided dice, and we assume that each of the 5 outcomes are equally likely. Then after 50 dice rolls, we get the following numbers for each of the 5 outcomes. Is that dice fair? Well, if you go calculate the chi-square from the previous slide, you get 12.8. Now, even though there are 5 possible outcomes, this thing is distributed according to the chi-square with 4 degrees of freedom. As we talked about last time, the overall normalization is fixed because of the fixed number of total experiments. And then you can just integrate this thing, again, as we did before, translate it into the CDF shown on the previous slide, and you get a low p-value, at least by my standards, indicating that most likely this is not a fair die. Again, if you're a real purist, maybe you'll say that 1% isn't low enough to refute the null hypothesis and you take more data. Okay, so that's what we discussed last time. Another hypothesis test concerns continuous random variables. So now you can't really write a discrete sum over a finite number of different outcomes. So how do you compare the data with the null hypothesis? Well, one way to do it, which is particularly elegant, and is the foundation of this KS test, is by looking at the empirical distribution function. So this function is piecewise continuous, and it merely counts the number of observations below a certain threshold, below its argument. So you can see that this shares all the desirable properties of a cumulative distribution function, namely the limit as n goes to infinity of fn of x, x goes to infinity of fn of x equals 1. Similarly, if you take the opposite limit, you get 0. So this is a real sensible cumulative distribution function, but it has the following form, generally, if I were to plot it. Let's say this is, say I ordered my observed data, x1 through xn, so that x1 was the smallest observation and xn was the largest observation. So what would the empirical CDF look like? Well, for x smaller than x1, it would be 0, right? There are no data smaller than the smallest one here. But then when I got to x1, it would go up to 1, and then it would stay at 1 until I got to x2. Oh, sorry, 1 over n. And then it would stay at 1 over n until I got to x2, in which case it would jump to 2 over n, and so on and so forth. All the way until we got to xn, and then it would be 1 for the remainder of the real line. So this looks qualitatively like a cumulative distribution function should. So let's say we made a model for what this cumulative distribution function should look like, and let's say that that model looked like this. Looks like a CDF, it's monotonically increasing, it stops at 1, fine. All right, so our test statistic for the KS test is going to be the maximum deviation of the empirical distribution function from the distribution function specified by the null hypothesis. It might look a bit scary because we have to take the max over all possible x, but in fact it's not. So I'll divide this absolute value into 2 cases. There's a positive case where fn minus f, we want to find that max. Well, it's just written another way. You can either have the largest value being where this thing is positive or where the reverse is positive. And in some sense, each of these 2 cases have to be treated a bit differently when you calculate this test statistic in practice. So at what points, looking at our diagram over there, at what points is this thing maximal? Fn minus fx. I think I see where you're going. I was looking for something even simpler than that. You just have to calculate the difference between the empirical distribution function and the modeled one at the measured values, right? We know that the empirical distribution function is monotonically increasing, as is the model. So let's look at this case here with x1. We might as well calculate the difference between fn and fx right here at x1, because the model distribution function is just going to get bigger as we increase x. So we test this point. Similarly here, look, the empirical distribution function is above the model distribution function. So we better test it here because it's just going to get worse as x increases. So you only have to test this guy only at x1, xn. So what would you calculate there? You calculate well, if we're at xn, then the value of the empirical distribution function is I. Okay, if we're at xi, so you know, like this at xi. All we have to calculate is I divided by n. That's the value of the empirical distribution function fn. And then we subtract the model distribution function evaluated at xi. That takes care of these points here. Well, maybe I should draw this differently for the sake of argument. Make this slope a bit bigger so that we have points where the empirical distribution function undercuts the theoretical one. That's this situation. Again, you only have to test at x1 through xn. But now we want to maximize the difference between the empirical between the model distribution function and the empirical one. Well, how are we going to maximize that difference? At what points is the difference between the line and the jagged line largest? Again, it's at the measured points, but we want to consider just before the empirical distribution function jumps, right? So let's take this xi as a test point. So it is here, right before it jumps, that the difference between the curve and the flat line is largest.
Xi is not the data set, right? That we already have.
Yes, xi is.
It's not one of.
It is. It's one of the measured data points that we have.
It is something just before, right? Something xi minus epsilon. Maybe.
Yeah. Well. Okay.
At xi it is.
Yeah. At xi it jumps, but this function has a discontinuity at xi. So, all right, xi minus epsilon. I feel like that's fine here. Assuming that the model distribution function is continuous rather than just piecewise continuous, that doesn't matter, but you're right. So what are the quantities we have to compare when we test this branch of the absolute value? Well, it's f of xi minus I minus 1 over n, right? Because we want branch before it takes the jump. Okay, so again, it's not too bad to calculate this test statistic. You just loop over all your xi, calculate that thing, calculate that thing, calculate the model of CDF, and then figure out which one's the maximum value. The problem is that the distribution of this test statistic is actually complicated. Again, we would like the CDF so that we can estimate a p-value using D, but I don't actually think that for arbitrary n, I don't think this is known in closed form, the CDF for D. If you go to asymptotically large n, you can show that the PDF, well, the CDF of the approach is this particularly simple form here. But again, that's only for asymptotically large n. Okay, questions about the KS test so far? This test is very useful, for example, in testing a random number generator that you might implement.
So how do you find the probability of D? Like you know the sample space of what does D can take, but how do you associate probability to each point?
Again, you'll get one value of D by finding the max value of X.
Yes.
And then if n is large and you feel like using the asymptotic formula, you can just plug it into here. This is your observed value of D. So you know that this is a CDF here, even though I've written it a bit differently. So just plug in your observed value of D here, and then you get a probability. However, that's a good question, and one which I illustrated with an exercise for you guys. So I'm asking you to write a program to do exactly what we just talked about and calculate this test statistic D. I give you some sample data, and I ask that the hypothesis be that the data is exponentially distributed with mean 100. It's pretty easy to write down the CDF for an exponentially distributed random variable, so you shouldn't have a problem calculating these different guys. But we only have, what, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 data here. So do not use the asymptotic form. I want you to do something else. Namely, you can use Monte Carlo to estimate the p-value. And this is kind of a general technique that you can use for a lot of different situations. So first of all, provided you had facility to generate exponentially distributed random variables, you could run what are called pseudo experiments. Right? So you have your data, and you calculate D on the data. Now we want to ask the question, what's the probability of finding a D at least as large as the one that we observed? Well, one way to do this is to just generate lots of data sets of size 10, where you draw 10 from an exponential distribution with mean 100. So generate many pseudo experiments and then on each of them